Very many thanks for a thought-provoking talk. The next talk is by Gabasova and Vitsarek, to be given by Gabasova, and it's a statistical investigation of magnetization of impact basins.
Okay. Mm-hmm. Okay. Just checking. Okay. Hi everyone. I'm gonna talk about the statistical classification method I developed for the magnetic signatures of lunar impact basins, the bulk of which I did in an internship with Mark Wicharek, but that I'm still working on improving. The main motivation for this project is that the magnetic signatures of impact basins record the magnetic field strength at the time of impact via remanent magnetization, and so taking a look at the evolution of that paleo field strength over time, so correlating it with the basin age, can let us constrain the time period when the dynamo causing the field was active. A project like this, well, studies like this have already been done, notably by Jasper Halikas about 15 years ago, but he didn't really try to quantify it, instead just looking at the radial profile and classifying it by eye, whether or not it was magnetized or demagnetized. My aim here is to provide this quantification with a robust statistical backing, and also to use new data, so data from the Kaguya mission for the magnetic field strength map, and also data from GRAIL for more accurate basin diameters. I'm studying the 74 largest impact basins, and about half of those have a relative age that we can look at. Either it's their geological period, or it can be a stratigraphic age group as developed by Willems in '87. This is the magnetic field strength map, and it's upside down. I'm very sorry about that. I caught it a bit too late. It was produced from Kaguya data by Tsunakawa and co-authors using a surface vector mapping method. This map is the field strength at 30 kilometers altitude, and the resolution is about 2 pixels per degree. There is also a high-resolution map available of the magnetic field at the surface, but the high resolution actually makes the statistical too sensitive, so we didn't use it. What we do with this field strength map is we look at each individual basin and sort the data into 3 separate bins. So we have the inner bin, so here within you can see on the topographic map, you can see there's the peak ring and the main ring of the basin. This is Mendel-Rydberg, that I'm using as an example. So we have first the inner bin, which is all the data within the peak ring, which we place for simplicity at 0.5 basin radii. Then we have the middle bin, which is all the data points between the peak ring and the main ring. And we also have an outer bin, which is data points outside the main ring up to 1.5 basin radii. To compare the field strength in those 3 bins, we introduce a number called M, which is just the ratio of the mean field strength in the inner bin versus the outer bin. The reason we're using just the inner bin in the peak ring and not the whole basin is that magnetic anomalies tend to be centralized and to just peak within the peak ring. This is quite possibly due to the fact that that is where the impact melt sheet is exposed, and that is quite possibly what is causing the source of the magnetization. There's a paper in review that talks more about that. So what this ratio gives us is the sign of the magnetic signature. If it's more than 1, then there's a positive signature. If not, then negative. But what it doesn't tell us is whether there is actually a significant deviation from the average. And to quantify that, we use a Monte Carlo method with synthetic maps. So what we do is we take the observed magnetic field strength map and look at the statistical properties of that, so mostly the mean and the variance, and use spherical harmonics to generate this random normally distributed map with the same statistical properties. And specifically, we generate 10,000 of those maps, and for each map and for each basin, we go to the basin location and get all the 3 bins that we used on the observed map, and calculate M for each basin, and for all of these 10,000 sets of maps. And this gives us 10,000 M values for each basin, and so we can look at the statistical dispersion of this set, which gives us a normal range for an M generated by chance. And so we can compare the real M value from the observed map to the cumulative distribution function of the synthetic maps, and look at the and so if we have a p less than 0.05, that the M value was generated by chance, then we define it as a magnetic anomaly. So this gives us magnetized basins and demagnetized basins. There is also the special case that is visible if you look at the radial profile of a basin. Sometimes there is a visible peak in the middle of it, but also the entire basin is demagnetized, and so that means the peak isn't really visible on the overall background. The way I interpret this is first that there was a shock demagnetization from the impact, and then because this happened in a weak magnetic field, we had thermal, probably thermal, because thermal is more localized than shock remagnetization, but we had some sort of remnant magnetization overlay on top of it, but too weak to be seen like in the other method we used. So what we do here is we define 2 other M numbers. First, one that compares the inner bin to the middle bin, and then one that compares the middle to the outer. And so this gives us, this lets us see whether there is an inner magnetic anomaly that is statistically significant, and also whether the entire basin is demagnetized significantly in comparison to the rest of the map. And so if both of these things are true, then we have what I call a weakly magnetized basin. With the having classified these basins into 4 categories: magnetized, weakly magnetized, no magnetic signature, and demagnetized, we can look at the average radial profiles of these basins, and you can see that they are quite coherent. So here we have the average profile of basins classified as demagnetized, which is just a depression. And then we have the weakly magnetized, where we have a depression and then a peak in the middle, and then the magnetized profile, where it is just a peak and no depression, and not much of a depression there. Now, if we look at those basins that have a relative geological age, here we can first put them by age group. We can here this graph shows the M values. I'm sorry, I keep pressing the wrong button. This graph shows the M values, and they are colored in according to whether or not the statistical method, whatever category they were assigned by the statistical method. So we can see that here in the Nectarian we have sort of an overall neutral magnetic signatures on these basins, with some magnetization, especially in the late pre-Nectarian. And then we have mostly magnetized basins in the Nectarian, with peaking in the early Nectarian there, that's age group 6. And then Imbrian basins are all quite strongly demagnetized. We have here average M values for these groups. So if we summarize this graph by just grouping them by period, we can see that all Imbrian basins are indeed strongly demagnetized. Well, all 3 of them, because there aren't that many in the 74 largest basins. Then Nectarian basins, there is a mix of magnetization states, but most of them are magnetized, or at least weakly magnetized. And then pre-Nectarian basins, there is also a mix, but those are mostly neutral. So if I compare these results with what Jasper Halakas did, mostly the results are congruent for 50% of the 28 basins that we both have in our relative studies. 50% of the basins have the same signature. Then 21.5% is where one of the studies did not resolve this weakly magnetized anomaly. So one study has it, for example, as demagnetized on neutral, and the other one has a demagnetized with a peak. And then 21.5% again is where only one of the studies actually found any anomaly at all. And then there are 7% where the sign is completely opposite, and those are slightly weird, but there are not many. And then also, if we look at Apollo data, there is a problem that crops up that Halleck has also noted in his papers, that the fact that all Imbrian basins are demagnetized doesn't really gel with the paleo-intensity measurements from the Apollo samples, which we can see there is actually supposed to be quite high magnetization in the early Imbrian. And the red shaded area is about the age of all the basins I studied, and here we have the pre-Nectarian and Nectarian and Imbrian, just for to relativize our study with the Apollo data. There are multiple reasons for there are multiple possible causes for this. Maybe the dynamo was working intermittently, and so that meant that it was actually not really working in the early Imbrian. Or maybe for some reason it was just stronger in the Nectarian, which doesn't really seem to show up in the Apollo data, but like it's not a complete global sampling anyway. Well, this is just something I can speculate on because we don't really know. And so to sum up, the main question that is brought up is why this thing is happening. Why do we have only demagnetized Imbrian basins when there was supposed to be actually really high activity in the dynamo? So that is definitely a question to answer. And I'm also planning to work on improving this whole project by first extending it to also smaller craters to have a larger data set, and maybe that would correct any issues with the small data sets skewing in their own direction. And also, there is just fine-tuning to be done, for example, using actual peak ring diameters for those basins where we have measured it, and also to look at the inner depression separately, because that is where the impact melt sheet is supposed to be visible. So maybe looking at that will give a more a stronger magnetization value. That's all. Thanks. I'll take any questions.
Many thanks.